Hey, what's up, guys? This is Chung here. So let's take a look at today's daily challenge problem. Number 923. Threesome is multiplicity, right? So this is a very interesting like threesome problem. This is like a little bit of variation of that. So you're given like an integer array, right, and the integer target. We need to return the number of tuples ijk such that I is smaller than j is smaller than k, and the three numbers, the three sum is equal to the target. And in the end, we need to do a modular for this one, right? So for example, right, we have this array of this one. So the target is 8 and the answer is 20. So how do we get 20, right? So we have a different of combination. So we have 1 to 5, 1, 3, 4, 2 to 4, and 2, 3, 3, right? So with 1 to 5, how many combinations we have? How many maybe occurrences, right? We have 8 because we have 2 1, right? 2 1 and 2 2 2 and then 2 5. So 2 times 2 times 2 equals to 8, right? So that's why the total uh, occurrences, right, for this 1 to 5 is 8, right? And then similarly for the rest, for the 1 3 4 is 8, and then 2 to 4 is 2, 2 3 3 is 2, right? So that's why in total is 20. Cool. And so the constraints, right? So the length of the arrays are like 3000, and the number range is only 100, right? Cool. So, I mean, for this three-sum problem, we can always try to solve this one with like a two-pointer technique, right? Which means that we will sort this array first, right? And then we fix the first number, right? And then we will try to use a two-pointer to find the remaining two numbers, right? But for this one, it's a little bit different because the um, there are few there are like a few uh, special cases, right? Let's say we have this 1 and 1, right? We are at 1 here, right? And then with two pointers, so we'll have like the left pointer pointing at 2, right? So and the right pointer pointing at 5, right? So from here, we want to know, right? So we know, okay, 1 to 5, they are they're like a valid tuple, right? But we want to know how many twos and how many five, because we don't need to worry about the ones here, because once we move to the second one here, we'll add like the similar number of 2 and 5 again. Basically, since we have 2 2 and 2 5, the total combinations for the second and third number is 2 times 2, right? Equals to 4. And so for the first one, we don't have to do the multiplication. We can simply move this cursors one by one, because the first time we had 4 and second time we'll also have 4. That's why we can also have 8 in total. And the problem is that every time when we find like a match, right, for the second and third numbers, we have to somehow move this cursor, right, because we want to know how many numbers, how many same numbers for the first number, for the second number, and how many numbers for the last number. That's why every time when we have like a match, we'll move the cursor, right, until uh until the next number is different. Then we can just use this count, right? This 2 times 2, and to find the total combinations of the second and third number, right? But there's like also special case for the second and third number, which is this like example 2 here. So in this case, the third, the second and third number, they're the same. They're both 2. So in this case, uh, what we have is simply the we have the combinations of the number. We have C42 in this case, which is the 4 times 3 divided by uh, 2 times 1, right? Which is 6 in this case. Yeah, so this is the only special case we need to be careful. So when the second and third number, they're the same, we need to use this formula to calculate that, right? And cool. So with that being said, let's try to implement the first approach real quick. To be able to use the two-pointer technique, first we need to sort this array, right? Like how we solve this three-sum problem. And then we have the number equals to length of array, right? Then we have the answer equals to 0. So for I in range of n minus 2, because we need at least two numbers for the second and third number, right? So we have num1 equals to array I, right? And then target. So the target is like what? It's the target subtract minus 1, right? And then we have left and right pointer. So left equals to I plus 1, right? And the right equals to n minus 1. That's going to be the two pointer. And while left is smaller than R, right? So we have a few cases. So the first one, if the L plus right is greater than the target, right? And then we simply decrease the right pointer. Else if the the total is smaller than this one, we increase the left pointer, right? And now we have else if here, right? So now the starting from here, right? We find a valid tuple, right? Here we just need to calculate. We need to check two scenarios, right? So the first scenario is like this one. If the current L does not equal to this one, right? That's the this 2 5 or 3 2 or 3 4 case, right? So in this case, we need to move the cursor so that we can find the total number for the current number, right? So that's why I'm going to have a count 1 and count 2, right? Equals to 1. So to move the left cursors, I do this. So if the while left plus 1 is smaller than R, right? And the left equals to the left L plus 1, right? And then we move the cursor. First, I increase the count by 1, and I also move the left cursor by 1, right? Similarly for the right, right? So while left is smaller than R minus 1, right? And then the R is equal to the R minus 1. And so for this one, I increase the count 2 by 1. And then I decrease the right pointer by 1. Okay. And then in the end, I simply do a count 1 plus times count 2, right? And then after this one, don't forget to also increase the left pointer and decrease the right pointer, right? So else what means what? Means the left, the second number and third number, they're the same. Then we simply need to use that formula, right? The total length of this one, which is what? Which is the R minus L plus 1, right? Basically, we have a total length here. So we have a length equals to R minus L plus 1, right? That's the total length of for example, this one, right? We have L pointing to here and R pointing to here. That's why the total length for this one is this. And if we use the second formula, that's going to be the length times length minus 1, right? and then divided by what? By 2, right? By actually this is 2 times 1, right? That's how we do a CN2, right? Cool. And yeah, and here we simply break actually, right? Because since the L and right they are the same, right? We don't need to move the cursors anymore, right? We can simply calculate the result. Okay, and then here I just do a return the answer after doing the modular with this one, right? Plus 7. Return the answer dot modular then is mod, right? Okay, submit. Cool. So it works, right? I mean, so for this, as you guys can see, so the time complexity for this one, obviously it's O of n square, right? Because we have a first for loop for the number 1, and then for the second and third, we have 2 pointers. That's going to be another O of n time complexity. That's why the total is O of n square, right? And so can we improve this, right? The answer is yes. I mean, if you look at this, the range for the number, so the range for the number is only 100, right? So which means that it gives us like another like, basically approach to what we can simply do a count, right? I mean, we can do a count for each of the numbers, which means that we simply do a count equals to the counter of this array here, right? And then we simply loop through all the possible combinations for different numbers, right? And for let's say we try all the possible combinations for the first 2 numbers, right? And then we have we have 3 cases. So the first one is the num1 equals to num2, basically n1 equals to n2 equals to n3. So that's the first scenario if we choose like 3 numbers, right? And then the second scenario is what? Second scenario is that n1 equals to n2, but does not equal to n3, right? And then the third one is n1 does not equal to n2 and does not equal to n3. So we only have these three scenarios when we try to choose 3 numbers from this count, right? And we just need to consider all the 3 scenarios at once. So what I mean by that is, okay, so assuming we have a count here, right? So from this count here, we have this count only stores the count for distinct values, right? So if we just select those first 2 numbers, the answer starting from 0, right? So we have 4i in count, right? And then for j in count, basically the I and the J are the first 2 numbers. They could be the same, right? So let's say if all the numbers they are all like 2, 2, 2, 2, right? And then the target equals 6, right? So in this case, we simply just select those three twos from this array here, and so that we can get 6, right? That's why I simply select I and J. Basically, I try all the possible combinations for the first 2 numbers, and then for the third numbers, we have like this target, right? Minus k minus I minus J, and we have this k here. So like I said, the first scenario is this one. So if the I is equal to J is equal to k, it means that we simply do what? CN3, right? and what's the cn3, right? That's the so we have a count I, right? And then times count I minus 1, right? Times count I minus 2 and divided by 3 times 2, right? And the second scenario is what? It's like this one. So there are two numbers are the same, but the third one is different, right? So which means I equals to j. So for this one, we have what? We have this one. We have this one divided by 2, and then we times k, right? Basically, we're selecting the do a c. We're doing like a c c this count I, right? cn2, which is this one, cn2, and then we times the third number, the count for the third number. And here I only checked I and j. I didn't, you know, but someone said, okay, so but n1 equals to n2 does not equal to n3. What? So how about n1 equals to n3 does not equal to n2? So how about this one, right? Actually, we don't need to worry about this one because as you guys can see, we are enumerating all the possible scenarios for this I and j, which means that the I and j could be n2, and there's another case where the I and j is n1 and n3, right? In that case, actually, we don't want to double count, right? And yeah, that's why we only compare the first two numbers, right? N1 and n2, so that when there's an n1 and n3 here, it's already covered because we look through all the possible combinations. So similarly for the last scenario, which means that n1 does not equal to n2 does not equal to n3. And how can we handle this scenario, right? So let's say we cannot use this. Basically, we cannot use this one. Right? We cannot do I does not equal to j does not equal to k. And why is that? Let's say we have 1, 2, and 3, right? So let's say there are like this three numbers here, and if we only use this one, right? Basically, 1, 2, 3 will count it, count as a valid scenario, and then 2, 1, 3 will also be counted again, right? And then 3, 1, 2, right? Basically, all the permutations of the three numbers, they will always be counting here. But actually, there are we should only consider those three numbers once, because the order doesn't really matter. All we care is the number itself, the value of the number itself. That's why we have somehow find to limit that. One way of doing it, we simply can do this. We always try to do a decrease, right? Or we do an increase, so that this one will basically guarantee that as for the three distinct numbers, we only count them once, right? And so for that, we have answers dot this one, right? This one count j, and then count k, right? So similarly, I also need to do this one in the end, right? So run the code, accept it, and submit. Yeah, so this time is much faster. And why is that? Because the value of the number is only within 100. So which means that the length of the count is limited to 100. So that's why we have this kind of so first we do a count. So do a counters, we have n here, right? So that's the n, and then we plus what? Plus the this one, right? A nested for loop for this distinct values, which is be 100 square. So that's the time complexity for the second approach, which is simply do a count, and then we consider all the scenarios, and and the only thing we need to be careful for the second approach is that we don't want double count the the combinations, right? For both for the second and third scenario. Cool. Yeah, I think that's pretty much everything I want to talk about for this problem. Yeah, thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.